Let's go.
Good morning and welcome to our first session today. We will have two talks in the morning. The first is by our host, Professor Raul Tempone. He's professor in applied mathematics and computational science here at KAUST, as well as Alexander von Humboldt professor at RWTH, Aachen University. He will be talking about uncertainty quantification across disciplines, wind and solar power forecast, and biomedical imaging. The stage is yours.
Thank you, Akko. Thank you for the nice introduction. Welcome, everyone. So today I'm going to talk about a few works that we have done in the group. This is a collection, and it entails many people. I try to be as precise as possible as we go through, right? And please feel free to stop me and ask any questions. So there are three cases that I brought for you today to consider using uncertainty quantification with a stochastic differential equation. Three applications. One is wind power, right? The second is solar power. They're both renewables. They have slightly different characteristics, and I hope I will show this a little bit through the talk. And as I show you a little bit of the application, I will try to show you a little bit of the techniques we used. And finally, which is a new one, and I think it's ongoing, is this biomedical imaging application. All right, so let's go directly to the first work, which is a collaboration here with Renzo Caballero, who's here at KAUST as a PhD student, Ahmed Kebayer, collaborator in France, Marcos Gavino, a collaborator from Uruguay, actually, Italian from Rome, and myself. So what's the problem, actually? The problem is to do uncertainty quantification on the path space. And what does it mean? Well, it means the following. You have, from the past, right, accumulated data. And what does this data say? Well, it says that you have always couples of pairs, couples of curves, essentially, for 24 hours or something like that. And these two curves are like this. One is the predicted curve that somebody computed using maybe a CFD code, and then some connection between the wind turbines and the power that they generate, right, to produce a curve that actually will predict the amount of power that a certain wind field will generate over the next 24 hours. This is never perfect, right? I mean, it has an error. So if you see here, the black curve for a certain date, say 24th of April 2019, is actually this smooth curve, black one, and the real one is this wiggly thing that goes around that is blue, and we call the real historical production, right? So to begin with, you have these couples of curves from many days, maybe 2 years. I think we collected like 2 years or something like that, with a frequency that could be between 10 minutes, 15 minutes to half an hour, right? So you have these couples of curves, right? So in principle, this is in continuous time, of course. You record it every a certain frequency, but the physical event is happening in continuous time. And then what is the problem? Well, in the future, somebody's going to give you a forecast, but you won't have the real thing. And in that case, you would like to somehow predict how much uncertainty the predicted forecast will have. But it's not just to put a band around this black curve, right? You would like to be able to generate statistically consistent curves in the path space, meaning continuous curves in the amount of time that the forecast goes, right? And these curves will be as many as you like, right? So you should have built an oracle that, given the forecast, produces as many curves, right, with the characteristics of the blue curves that you collected in the past. So, and what is the real characteristic here? It is the difference between the blue curve and the black curve, the prediction error, right? This is what you have collected in the past. Are you going to improve the model like that? No, you're not, okay? So this is going to be a phenomenological approach where actually we try to build uncertainty quantification on top of an existing forecast. We're not going to improve it. We don't know from where it comes, right? So this is going to be phenomenological. We are not going to use any physics. The information is going to be limited to some prior information. For example, okay, power can never go negative. Power can never go above the installed power, right? Even if you get the best possible scenario, you can get a maximum amount of power. So that's why this is normalize to 1, right? Because we know the installed power, the maximum capacity of the system. And we can always kind of, relativize everything to it. Now, some things, therefore, will be known almost surely, right? No curve should leave the interval 0, 1 if you're working here in 1D, right? And that we should impose a priori, right? When we build the phenomenological model. This will mean that if we are going to use stochastic differential equations, we have to impose some conditions on the drift function and on the diffusion function. That's what we have to do, right? Now, we want other properties. For example, okay, you give me a forecast and I'm going to put uncertainty on it, and I claim that I'm not going to improve it. I will take it as it is. So what does this mean somehow? Well, in our wording, it means that our uncertainty quantification should be centered with respect to the forecast that you're giving me. So for any time, right, if I compute the exact mean, cylindrical mean, I fix the time and I take an average, right, of all the possible paths, I should be able to prove that actually my SDE model is centered on top of the forecast that was given to me, okay? So the stochastic differential equations that we're going to provide then are parametric on functions, right? So the input to this is going to be the forecast function, which is a continuous, actually, differentiable function over some interval on time where we want to do the analysis, right? And given this input, with some parameters that they're going to fit, we should be able to produce uncertainty quantification. All right? That's the game. Is that clear? Good. So practical. There are things that are a headache here. So people in principle say, oh, you can't control renewables. Of course, wind comes, right, and produces something. If you have the wind farm, it's not like a fuel-based generator where you can actually tune the power to a certain level. But actually, you can shut down things, right? You can just impose, okay, this guy is not going to generate anything at all. You just block the movement of the turbine, period, right? Sometimes, as you wouldn't believe, but actually sometimes we have too much power. And if we have too much power, some bad things can happen in the system. So you need to shut down things. And this is called curtailing. And this is man-made. And if you see, I'm trying to predict an error, which is a prediction error, that does not include this man effect, right? Man-made effect. So in some sense, the data has to be cured before you actually pass it to this fitting that we're going to do. Because if you put this curtailing in some periods of time, you will have a huge prediction error, which has nothing to do with the physics, right? So, okay, one has to do it, right? And then there are some kind of lines of work there, automatic detection of curtailing and other things that one can work, and we're doing. But that's another story. So in principle, all the data that I'm going to assume here that we have has no curtailing. So the error actually comes from the physical prediction between what the CFD plus turbine things would predict and the actual reality. All right? So stochastic differential equations. Okay, I teach a course on that, so you can come to listen to that if you have not seen it before. This is like a generalization of an ODE, if you wish, where the first part is the familiar part to you, where you have the drift, right? And if you would have only this would be an ordinary differential equation. But you also have this other part, okay? And this induces noise in the trajectories of the system. Not only that, it changes the regularity from being, say, almost infinitely differentiable here in the ODE to something that is held just almost 1/2, almost, right? So it has a lot of effects, but you can still do numerical analysis, you can still do numerical simulation, and everything goes well. Even if you thought before that all these functions that are nowhere differentiable are pathological, no, actually they're very useful and they're very practical, actually. So in SEEs, right, we take this A and B as given. Here we twist a little bit the thing, as you saw before, there were talks yesterday where we have a parameter theta, right, that you wanted to infer using data, right? The addition here is that you also have this parametric dependence on a function, not just a parameter, it's a function. The function is given to you. This is P, the forecast of the power that you're going to expect to get in the next hours, right? And also just, redundantly, of course, we add here the derivative. Of course, if I have the function, I have the derivative, but okay, it's just notation. All right. Of course, we assume that these two are consistent, right? But anyways, it's just notation. So what is the game here? First, I'm going to explain you how we choose this A and B, right? Depending on the parameters, what is the dependence on the P, right? And P dot. And then we will do the fitting to find the theta. And of course, in the process, we will try to kind of explain a little bit of the theory that is behind to ensure that everything is well posed. You have an initial, you have a unique solution and so forth. Okay. So what about the drift? Well, the drift is responsible actually for keeping this centering property. So as I was telling you, I would like this X, which is going to be stochastic, to essentially be centered around P, meaning that if I fix it any time, the expected value of X should be P, right? Okay, this guy is coming from a Wiener process, right? It has mean value 0. This will induce some martingale properties here. So essentially, this guy will not play a role in that centering property. This will, okay? So in this case, a choice that that works for this A is just to use the derivative in this following way. And just by using Ito formula, you realize that after you choose this, leaving this as a parameter to later do inferencing on, you get the centering property, okay? So if V actually is the difference between X and P, which is the forecast error, the expected value of V should be 0 for all times, right? Of course, making the assumption that at time 0, this V had expectation 0, okay? So this is the right choice for that. And now this theta, which I leave it as a function, is going to help us actually to fit some properties of the observed data. All right, so if you don't do that, for example, and do not have the derivative here, you do not have the centering property, and that, for example, will have some bad properties. For example, it will be difficult to create bands of confidence. The bands of confidence will not really behave nicely. You will have some kind of delay effect. But if you add the derivative, actually things work quite well. So it's really important to add that term. Now, what about the second term here, right? Well, this diffusion part will actually help us to keep the paths within the interval, in this case, 0, 1, right? So one particular choice, and I'm going to emphasize the word particular because we're later going to generalize that, is to choose this B as the square root of some coefficient here times X and 1 minus X. Okay, this is not a coincidence, right? This function vanishes at 0 and 1, precisely the points that we wanted to keep as hard barriers, right? Or sure barriers. Okay, and that through the theory will ensure that trajectories do not cross those boundaries, right? Because at those points, the drift will be pointing inwards into the domain. So this will do the job. Okay, so now you can actually show existence and uniqueness and other things. We're not going to stop on that. We need to actually ensure some properties on this theta t function, linking it with the P, the forecast, and some parameters that we included, right? And yeah, these parameters will be alpha and theta 0, and this will appear throughout the whole talk. I think I'm not going to change the notation with respect to alpha and theta 0. Alpha is going to be connected to the essentially how thick is this band of uncertainty around the forecast, and theta 0 will be connected to some speed of mean reversion. Okay, but if you see here, there are some nasty things here appearing, like 1 minus P and P, and this in principle could get to 0, right? And you could have some nasty effects there. So one has to regularize a little bit, and that the way to do it is to truncate the prediction function. Don't allow it to get too close to the boundary, right? Neither to 0, neither to 1, by introducing this epsilon, and then using this epsilon as a parameter that you also fit in the model. So two things happen here. Epsilon guarantees then that the X does not reach the boundary in almost surely infinite time. That's good, right? And we don't excite that singularity. And then it allows us to do a better fit as well. All right, so this is now the model as we have it. And then we build a likelihood. Now, the advantage of what we have done now is that the model is Markovian. So when you want to fit, this will be easy, provided that you have a good hold of the transition density, right? And as we saw yesterday in some of the talks, most of the cases, this transition density is untractable, or at least you cannot just write it in closed form, right? So what do? We do what is called, at this level, later we will generalize, some indirect inference. And indirect inference is that you're going to put something that hopefully approximates well the intractable density by choosing a certain family, right? And fitting it using, for example, a matching moment method. The advantage of this model is that by Ito, you can compute the moments of this V function here in terms of ODEs. So you can actually approximate very well as many moments as you like of this V function, but you cannot track, but the density is still intractable. So you use this information from the moments and some particular choice of an approximating density, and then you fit that. What have we done? We have done, for example, beta, and beta actually is good because you know that actually this V is bounded, right? You know the interval where it lives actually, and therefore the beta gives you a lot of flexibility to fit this well. Okay, so I'm not going to bore you with the likelihood in this space. I mean, we are using the fact that we have the transitions, right? And these transitions of the error essentially are used to build up a likelihood that essentially using assumptions of independence has a multiplicative structure, and then you take the log, and then you end up in a classical optimization problem. And this is what you solve, and then of course you get the results. We have some tricks to produce good initial points for iteration. I'm not going to stop on that. And I'm not going to walk you through the exact computation of the moments using Ito. But as I told you, we can actually, once we have the moments, we can have the parameters of the beta distribution, and using that, we can compute this approximation of the log likelihood. So we do that, and we use this in optimization. And of course, if you write the gradient of the log likelihood, right? This is a sum over, say, time steps over a day, data of day, and these time steps, as I told you, could be every 10 minutes for 24 hours, for example. And you have many days. How many? Maybe 2 years, right? So this is a long sum. So in order to accelerate the optimization, it is natural to randomize here, right? And instead of just computing the whole gradient, use a stochastic gradient version that will, for example, be the door to use, I don't know, stochastic gradient descent, Adam, or all the techniques that Carlon is going to tell you just after my talk, right? With the stochastic quasi-Newton and so forth. So this produces a huge advantage in terms of computational time. It's just that you have to be careful here in the computation of the L and its gradient, essentially, because you have paths, right? So you have to actually compute sensitivities of the paths with respect to the parameters. So this means taking first variations in the ODEs that define the moments in this approximation that I told you before. So this thing is here, but I'm not going to stop either. You can discuss it later if you want to. And well, this gives us an unbiased gradient estimator. We use it, and actually, if you compare, for example, the method that does not use the randomization and does not use the gradient, you essentially can save a factor of 100 in terms of speed here. So this is not a joke, right? It's a huge deal when you try to react quickly. This is part of SAFE's thesis, master thesis that is going to be defended soon in June. Yeah, we're getting there, right? Great. And there are more things that you can do here. For example, whenever you do a computation, right, there's a lag time between somebody does a computation knowing exactly what the power generated at this moment is, and this computation goes to the analyst that is going to use it later. Maybe there's a delay of 1.5 hours, 2, something, right? But this means that at time 0, when somebody's using this forecast and the uncertainty, this thing should not have an uncertainty that is negligible, right? Because, I mean, I compute here, right? And in the moment that I compute, my error is 0, but I let some time go by, right? And then my uncertainty should be non-negligible. So when somebody has to start another computation, he or she should have an idea what is the uncertainty here, okay? That can be done. There's a trick here to do that, and you can actually estimate and then come back to the engineers and say, hey, it looks like you do usually your computations 2 hours before you actually pass it, and they look at you like, it's impossible to do that. But yeah, it actually works well. Okay, so then what do? You try to estimate the goodness of the fit, right? You try to check how the actual error forecast errors behave with respect to what the model predict. You are there, but still things can be improved. You can compare against previous models that, for example, didn't have the derivative tracking, right? This is something from a previous master thesis here too, and you get by the classical, model comparison techniques, an improvement using the new model. Of course, that's to be expected. The good thing also is that you can even discuss and be quantitative about the following situation. You have one company that is buying forecasts from 3 providers, for example, and the company, the electricity utility would like to know which provider is better, right? I mean, they have some idea, but I mean, they would like to have some comparison, and you can do that too, right? Using these techniques, you can compare. And of course, as I promised, you can also generate as many paths as you like in the path space, right? So this could be used, for example, for stochastic optimization when you generate the scenarios. But most importantly, when you want to do continuous time, continuous space type of optimization using Hamilton-Jacobi-Bellman or approximate dynamic programming techniques. So yeah, it really works, and it gives you something that is useful. So I think I told you that this was a phenomenological approach, right? We didn't use the physics, so we don't really know where the actual wind farm is or what is actually the wind that is flowing there. We just have an idea of what happened in the past with respect to a family of forecast. Somebody gives us a forecast, we provide the uncertainty, okay? So it's really cheap. Once you have the SDE, to generate this path is absolutely no cost at all, right? So that's very, very useful indeed. Okay, so I told you about the optimization, right? Now let's go to the solar power. That was the work of Paula Benjamin and the rest of the team. She did defend her master thesis at RWTH in Aachen recently and moved to Deutsche Telekom. So she's not in the academy anymore. So what happens here that is different from what I told you before?
Question here. Did you try some different methods to forecast time series? So you use this ODE approach, stochastic.
Yeah, this is continuous time, right? I want continuous time. So time series is discrete time.
Okay.
So those are out. Yeah. Yes, I told you that I didn't stop on that, but you have different providers, for example, and these providers are using maybe different forecasting methods. They don't tell me. They just say, I'm provider A, I'm provider B, I'm provider C, and I have to judge essentially based on this kind of techniques, which one is better. This we can do. But again, it's totally agnostic, right? You have no clue how these computations are done. Maybe somebody's doing like this, right? And then maybe he beats the others. I don't care, really, I don't care. He produces a curve and I judge it. Okay? Okay, so what does it change in solar from wind? Well, in wind, I told you, there's a maximum value that you cannot surpass, right? Okay, so, and this can be more or less attained at any time of the day, depending on the day of the year and the characteristics of the atmosphere. With solar, this is not the case. If you want to be sharp, you have to take into account which day of the year this is and what time of the day this is. Why? Because, sun goes up and down. There's a certain angle, right, of incidence, and that will change the maximum power that you can attain at any point in the world. And that somehow is this orange curve. This orange curve was produced, and actually was part of the work actually to produce it, to be able to fit this thing at all times. Because I tell you, again, we only use the data. We are not being told, for example, what is the latitude the actual solar farm. So if we don't have this information, and still we should be able to produce this orange curve. What what happens also with respect to wind? Solar has a much shorter time scale. So if you see the curves of the real solar production, right, they look way nastier than the other, right? I mean, the other like was wiggly, but essentially didn't have this kind of sudden moves, right? So this is also something that will characterize the solar. So what do you do here? Well, you bring it back to the other problem somehow. What do you do? Well, this HT here is the maximum power that solar can attain at any time of any day in the year. And what are you going to do then to scale X by that H? Essentially, you will divide by that H now, and naturally X now will live in the interval 0, 1. And then you bring things in some sense to the previous case. It's a little bit more entangled, but you still bring it. So again, you postulate a drift and a diffusion. By the way, how am I doing with time? Yeah, okay, good. So you postulate the drift and the diffusion similar in the same way to keep the centering property and also the property of not leaving the domain. Okay, there's some theory to back that up, to provide the existence and uniqueness of the paths, right? That is there. You have to again satisfy some properties of this theta t function with respect to the parameters that you're going to play with in the inference. But if you do that, everything's going to be guaranteed fine. All right, so what else? The truncation, we told you before. The likelihood is exactly the same, but it's going to be a little bit more wiggly in terms of this, if you understand this HT actually should go to 0, right? As we approach nighttime, right? So now you're scaling by something that goes to 0. So you have to be careful, right? This didn't happen in the wind. So that is one of the features that makes this a little bit nastier. But again, you can still do the moment matching technique and do the optimization. What else can you do, or did we do? Well, here's the application of the actual solar. And you can wonder why I'm choosing Uruguay. Well, I have personal connections with Uruguay, but also Uruguay is one of the leading countries in the world with respect to the penetration of renewables, right? So sometimes it runs completely in renewables. Okay, so that's pretty much it, right? You have optimal estimates. That's using the same things as we did before, right? With the stochastic optimization and so forth. We checked just by using different data sets, right, that the parameters recovered were stable. That's not a problem. And yeah, here's some isolines of log likelihood to convince you also that there's nothing strange here in terms of global optimization, and also to convince you that the choice of the initial point that we're using for the starting point of the optimization algorithm is actually pretty good, right? This start doesn't need any iterations and is based on some theory, but it's actually pretty good. What else? Okay, this is sort of the results, and as you see, the paths that we now generate not only kind of almost surely stay within the orange curve and the 0, right? But also exhibit this kind of nastier type of behavior that the blue actually paths do show, right? Even though the forecast is a pretty smooth function, right? So you see here that these red paths are capturing characteristics of the blue, right? That the forecast doesn't even know about, right? So that's important as well, because again, if you want to generate the scenarios, these curves should have the characteristics of the actual historical power, right? In terms of correlation, in terms of other things. And this is automatically captured. And of course, if I change the forecast, these curves will change automatically without having to recompute the parameters. That's the beauty of it too, that you just give the input as a curve, right? And automatically comes out this uncertainty quantification. Okay, you can have the confidence intervals, but that's not so exciting. Okay, now an extension, and this is part of Saif's thesis that is going to be, my master thesis that is going to be defended soon. I said, not only he made a faster optimization for these fittings, but also he studied the generalization of these coefficients. I mean, when I introduced this diffusion coefficient today, right? I told you that this diffusion coefficient was responsible for keeping the paths in the interval 0, 1, right? Because it vanished precisely at 0, 1, and then the drift was pointing inwards, so nothing escaped. Okay, but I said this is a choice, right? And you could say, okay, but why did you choose a square root? Okay, because I mean, it's a classical model, that's why, but we could have generalized this to some other power, right? Beta and gamma, and fit those as well. Okay, and then you say, well, but okay, this is any theory, can you actually do any beta and any gamma here and feel safe that you have still existence of uniqueness? Actually, no. Okay, so if you want to really be sure, you put a bound here of 1/2 from below, and then see what happens. Fine. If you do that, you go and recover here this power, and the power is not exactly 0.5. And then you say, okay, if we compare with the previous model, do we have an advantage? And actually we do. If we actually compare now the error transitions, and we see the data, this is a KDE, right, in 1D, the blue one is the data, the orange is the one simulated with the square root, right? Okay, you see that it has some misfit here and some misfit here in the tail. But if you actually leave this beta and gamma now free, you have something that, okay, still not perfect, but goes in the right direction, right? Approximates the blue density better than the orange one. Okay, so can you do even better? Well, one way to do better is to say, okay, I said that the transition density was not tractable, and I took a cheap way out. What was the cheap way out? Was to say, okay, I'm not going to compute it. I'm going to essentially assume that the times between observations are relatively short. So then some kind of approximation by a Gaussian or approximation by a beta will be decent enough. And the fact that actually I have the exact moments allows me to do a fit, and I do not need to compute, you know, the exact value of the density anymore. I just go with this approximation. Problem is that, you know, if you do that, you don't have an error that goes to 0 in some way. You have made a choice and you stick with it. And then you say, okay, can I improve this? Well, that would mean evaluating the exact density. That would be costly, because if I have to do a KDE, for example, that would be costly. But you can do a KDE coupled with control variates, in which sense you're going to reuse the sort of good approximation based on these moments from this sort of approximating density, and use it as a control variate with respect to the usual KDE. But that entails something more. I mean, if you have a density that you have computed and you want to use this as a control variate, you need to actually be able to generate paths that are consistent with that density. Okay, because otherwise you will not have the telescopic property from this control variate. So what do? We actually create an SE that is consistent with the density that we seek, and we use this to control variate the actual true paths that we seek, and that actually allows us to actually now provide, you know, a confidence interval for the density at the points that we need for the likelihood, right? And yeah, we can now have a, you know, consistent method that, if we provide enough information, will be as accurate as we need. Okay, so how much time do I have?
5 minutes.
Okay, yeah, all right. So I think there's not much more to say. I've said it through. Let's go to the last part. Okay, so this is the recent thing. I'm just trying to show you that this works in more areas, right? And this is the heart's left ventricle volume, right? So why is this problem important? Well, if you measure the volume of this little thing inside of your heart, you can actually detect hypertension assess cardiovascular mortality, and even diagnose heart failure. Okay, so this little indicator can provide a lot of things about you. So, okay, before one would get sort of layers of scans from an MRI, some particular guy will sit down and manually do the sort of identification for each of these slides of where this part is, right? And then measure the area, then sum up the areas, multiply and put some certain width, right? And then get an estimate of the volume. Fortunately, machine learning algorithms like UNet do this automatically, right? So you pass essentially the MRI slice, and they will determine what is the area. But they're not perfect, right? They can make a mistake. So how big is the mistake? Can we trust this with your heart? That's the issue, right? So this is exactly what we are trying to do here. And this is an ongoing work in Germany with Felix, who is a PhD, and Achim and Philip, who are in DLR, in the Institute of Software and Technology. And actually, Felix has recorded an online presentation for his poster. So I suggest you go and look at it online. So as I told you, the deterministic way of doing this is to run the machine learning algorithm, right? The UNet. You provide each of these slices out of the MRI. It will identify where this thing is sitting and will kind of estimate the area, multiply times the width. And by the way, the width, in the width direction, you have more error than in this flat thing. So you always try to kind of find the shortest distance when you do the MRI. Okay, and then you sum up, you produce one value, say 52 milliliters. That's the deterministic answer. What do we want? We want to do something like this with the same information, right? And knowing from the past, by comparing, say, the outcomes of the machine learning algorithms versus the outcome of labeled data produced by humans, right? You would like to actually produce something like this that says, okay, yeah, sure, it's 52 milliliters in some sense, but it's actually a distribution, and this distribution may even have sort of some bumps here and there, right? It's not even unimodal. Where is this bump going to come from? We can still explain it, but this is the kind of thing that we do expect actually out of the machine learning algorithm. By the way, before we continue, this algorithm, the one that is used, does not know that you're computing a volume. It just knows that you're computing areas, right? And then you sum up stuff. So it's not using the fact that actually these areas that you're computing are connected in some sense, right? Because I mean, the heart is changing in some sense continuously, right? As you move in this direction. So I told you the whole standard is to manually segment and then compute the thing, right? Machine learning has taken over. And which are the problem features that we see here? Well, for each medical center, we have limited amount of data that we have accumulated during the past, and we cannot afford training a predictive neural network with 20 million parameters, right, from scratch. So we therefore try to use a pre-trained network for the segmentation, and here's a reference for that. And then, again, not saying we're going to prove anything here, focus on calibrating the SE for the UQ on each medical center, right? And then providing, once you have a new patient, providing immediately the uncertainty quantification for his own prediction without having to recompute anything. So I told you segmentation task is just volume prediction, right? So what you do, I mean, this thing will get the MRI, and then we'll segment this in these voxels, and we say, okay, this voxel is in, this voxel is out. You will count the voxels, sum up to get the area, multiply times the width, and then do this for many slices, and then you get an estimate. So how does it work then? If you look at the scale, the area here, say you have the first slice, which will mean when you're starting to touch maybe almost the left ventricle, right? Then the cross area is 0. Then suddenly, as you go into the volume, right, you start cutting, and then this area starts growing, right? And this is sort of the thing that you see here. And then at the end, you die out, right, by exiting the part of this volume. Okay. Now, how do we make the connection with the previous thing? You say, fine, there is something that is going across the slices, right? It's my volume. This process is happening, say, from left to right. I mean, I'm doing the scan from left to right. Why not using the slices as fake time? If we do that, essentially, This connects directly with what I told you before, right? So now time is the width, so it's the depth of the left ventricle somehow, right? So now you have this curve that is being predicted as we had before with the power, but this curve is a cross-sectional area that the machine learning algorithm is predicting. All right, but then if we have that, we can still postulate some AZE that is going to be centered around this this prediction and go with it. Okay, not so fast. Why? There's something weird here that doesn't happen with the power. Think of the following: you have this object, right? You're trying to measure the volume, and what you do is to actually cut it and look at the areas. Everything's okay here in the middle. Why? Because the uncertainty mainly is in the boundary, right? I mean, these guys that are in the middle, they're not disputed, correct? But if you get close to the boundary, right? There's one slice where you're actually going from in to out. And then maybe a whole chunk can suddenly become uncertain, right? Not just the boundary, but you know, you're going to exit almost, and then here, for example, you have an expert label, and he says there's nothing from the left ventricle here. But the protein network, right? State of the art says, oh, but we have actually a piece here. And you know, it's not a negligible thing. You multiply times the width, and then you get a volume error that is not minor. The opposite can happen too. You know, the expert says, oh, but you have here something, and the network says there's nothing, right? So something happens at the boundaries that doesn't happen in between, physically, just by construction. And you have to, you know, you have to take this into account. The way to do it is actually to do a stochastic differential equation that has no jumps in between, and then at the beginning, the first slice and the last one, introduce a jump measure. This jump measure should be exactly on the first and on the last. Why? Because, you know, you should be able to get the same error and the same volume if you go in this direction or in this direction. This is not physical time, remember? So if I stack a bunch of figures, right, like these slices, and I compute areas and do it in this direction or in this direction, it shouldn't change. Otherwise, your method is like weird, right? Okay, and this is the kind of answers you can get, right? As I told you before. And we also do size effects, right? I mean, what do you expect? Well, to do these computations, we normalize, right? So we essentially divide by the predicted volume, right? And do this uncertainty. And then, of course, what do we expect? If you normalize, right? And the resolution of this neural network and the device that you're using to measure the MRI is fixed, the smaller the heart, right? The larger the relative error you will have, right? Because you're measuring a volume that is smaller, right? The resolution is constant. The smaller this is, the larger the relative error. Okay, can this fit capture that? Of course it can. You have to just bin the data according to the predicted size of the volume of the left ventricle, and then automatically the parameters adapt to that and predict it's as effective that there's larger relative uncertainty in smaller hearts. Here, for example, is a binning with 8 groups, and here's a binning with 16 groups, and it's consistent, right? I mean, this is going with the parameters in the right direction. We also do the following. We say, okay, let's train it. I mean, let's do the training of this SEE using this direction for the SEE, the fake time. And let's train it also using this direction, the opposite. Does it change? Well, not really. I mean, the variability is of the same order as you will have if you say split the data in different groups. So this is fine. The method actually is insensitive to which direction you're using it, which is physical. So I'm getting to the end of the talk. So as a summary for this part, I told you accurately measuring the left ventricle volume is crucial for detecting hypertension, another bad thing in your heart. So if somebody's telling you what is that volume, he or she should be kind of sure what it's saying, right? And if just a number may not do the trick. Machine learning algorithms like UNet have allowed for better automatic segmentation, but we still need to provide uncertainty, right, to their outputs. We model the prediction error with stochastic differential equations calibrated with labeled data. We validated the robustness with respect to different training data. which reproduces this volume error multimodality that comes out precisely from the jumps that occur on the first slice and the last slice. They are responsible for these little bumps that you see in the distribution. And we verify these predicted volume size effects, right, in the U2. I told you that we introduced these two independent jumps to take into account the larger errors in the first and last slice. And this is cheap. If you look at a neural network, right, of this kind that is so precise, it has 20 million parameters, 20 million parameters. A naive way to do that is to say, okay, let's randomize the parameters. This is done in literature sometimes. Let's do Bayesian stuff, right, on these 20 million. Okay, good luck, right? There's no way to do that. But this approach has only 8 parameters. So it's pretty quick it is not data hungry, right? Particularly good for, say, small clinics that do not have the access to huge data sets. And they have, somebody was telling me actually that it's not just the MRI, the machine, right, that will produce a certain output. It's just the way they do it. I mean, the actual guy that does the tests, right? So the coupling of the actual guy and the machine produces a certain level of error in the prediction of the volume. Therefore, same technology, say Siemens put in one clinic and Siemens put in another one, having, say, a seasoned guy versus a young guy will not give you the same uncertainty. And therefore, there's value in doing this, right? Having just few data and adapting to the different certain circumstances that your doctors may have. All right, so I think that's all I wanted to say. Thank you so much for your time. And yeah.
Okay, thank you so much for the very nice talk. Do we have any questions?
Hi, thanks for the talk. I have a couple of questions. I noticed that in the SD model that you have the 2 parameters alpha and theta 0, right? And I've noticed that in the model, they both always come together as a product.
It looks like, but it's not. Actually,
okay, but why do you split? Yeah, that's what I'm not sure why you split it into 2. You can just
very good question.
Do a parameter estimation over one parameter, right?
Yeah, I mean, if you look, where is the theta t? There's a theta t choice. Has its maximum between theta 0 and alpha theta 0 with some other stuff, right? So this automatically decouples the theta 0 from the product. Here, theta 0 appears alone, right?
Okay.
And this comes from this theory, right, that requires the control of the path. Do not get too close to the boundary because then you have some explosions that have some issues, right? If you don't have these boundaries, right, automatically here you will put theta 0. I mean, this is the most naive model. Theta 0 here. So theta 0 appears here alone, and then alpha theta 0 appears here. You could say, okay, why didn't you call this another parameter? Well, because I'm motivated for certain things, right? And as I told you, if you put theta 0 and theta 0 here, well, this is controlling actually the mean reversion rate, right? While alpha is controlling the width size. So I have an interpretation of what alpha is and what theta 0 is if I keep it in this parameterization. But it's not a unique parameterization, of course.
Okay.
Okay.
Yes, and another question. I think you also when you use the moment matching to estimate the parameters.
Correct.
You have to solve an ODE.
Yes, that's right.
Yes,
you can solve any ODE solver that you want, right?
Yes, but are you also considering the error produced due to these approximations in the final error of your?
You can overkill that much cheaper. I mean, you can overkill the ODE error.
Okay.
With almost no cost in comparison to the other error that comes from those statistics and simulation of ACEs and so forth.
Okay, so it's negligible compared to the rest
with respect to the others.
Okay.
Normally, by the book, you should entail everything, but we prefer to actually overkill it with respect to the other, and then it's one error less, at least to deal with.
Okay. Okay, thanks.
You're welcome.
Any more questions?
Thank you for talk. How easy is it to reapply your techniques from? So a question about your first part of your talk. How easy to reapply these methods, techniques for Germany or Tuval not to Uruguay, but to another.
I mean, the last technique was medical, right? Has nothing to do
No,
with
about first part of your talk, not about.
Oh, the first part of the talk.
Yeah.
I mean, we have data from France also. We can use it there. This is not geographically dependent or anything like that. We are not using anything that is geographically dependent.
Okay.
No.
So this is
easy.
Okay. Good.
You know, each provider can vary in terms of the frequency that they have. The higher the frequency for the data, the better for us, right? Because the better, for example, for these surrogate approximations of the density, the transition density, and so forth.
Sorry, and about your answer, why do you need continuous on not discrete time series? Why? Because I'm thinking in discrete times, days, hours.
Physics occur in continuous time. Okay, so the physical process here comes in continuous time, and my particular motivation also is that I want to do stochastic optimal control on top of this, and therefore I don't want the time series or anything like that. I want something that I can use, and I can choose my delta t in any way I want. So therefore, it has to be continuous time, because then I will use it for discretizations of some other kind, maybe a nonlinear PDE or something like that. But I need to have it defined everywhere for all times, for all state.
Thank you.
You're welcome.
Any more questions? Okay, so I was thinking about these different labels the experts put on the measurement, right?
Mm-hmm.
So have you tried any multi-fidelity model depending on the reliability on the labels, right?
Depending on the reliability of the label.
I mean, there must be. I mean, if you cut out the heart and measure the volume, you get an exact, very reliable volume, right? And then there can be different experts putting labels. Okay, this is, you show that the machine learning model mistook, cannot, and then you have, I mean, there's different accuracy in the...
In here, in the procedure, there's a tacit assumption, right? That the data comes from one source. If you have two sources, you will treat them differently and then try to conclude which source is better. But as far as I have done, we have not mixed different sources of data.
Okay.
So that is more or less the, the approach, right? That you want to kind of analyze, for example, this combination of machine and one guy, right? In this MRI, it's just one thing. Machine with another guy is another thing. And I would like to kind of do things tailored to each of them.
Then about the
I mean, it could be done the other thing, but we didn't do it because the problem does not require it. But you could mix data, and in some sense, you will have to do slightly different.
Then the power sources in Uruguay. Now you showed about wind and solar. So what are the other power sources in Uruguay?
Hydro, for example, is very large.
Okay.
Hydro.
Okay, so could that provide like a lower bound in this? You had an upper bound and then there are the confidence intervals. If you could, do you get what I mean? I mean, if you...
No, because I mean, we do this uncertainty quantification for each of the sources alone. So say when I analyze solar, I'm not looking at the others. What you could do, and this is something that we may do, and we have ideas how to do it actually, is to do, here I was doing, say, a 1D type of analysis, right? I mean, you have power with respect to time, and then you could say, okay, could you generalize this to a multivariate version where you have, for example, solar and wind together, but as a vector, not as a sum, right? And the demand maybe of the whole country is 3-dimensional. Each of them come with a prediction curve. So now your prediction error is in 3D. And then the transition densities, right, now are in 3D. Okay. If you use naive techniques for kernel density, for example, which is one of the techniques I was using here, this will not work as you start raising the dimensionality of this observational vector, if you wish. But there are ways to deal with that as well. But we have not kind of written that yet.
Okay.
Yeah.
Let's thank our speaker again, and let's have a...
Thank you.
Okay, we'll have just a 5-minute transition to the next speaker.